Hello student, my name is Kalal from LJ Institute of Engineering and Technology. Welcome to my online lecture series of refrigeration and air conditioning subject. So today I will discuss the part 2 of air refrigeration system. In part 1 we already discussed Brayton cycle, reverse Brayton cycle and their numericals. Brayton cycle and reverse Brayton cycle are normally used in earlier of years. Okay, now air refrigeration system, this part 2, which is used in aircraft system. So let's start to discuss first topic, that is a simple air refrigeration system and simple air refrigeration system with evaporative cooling and bootstrap refrigeration system. Let's start to discuss one by one. First is simple air refrigeration system. Okay, this is our diagram for simple air refrigeration system. So what happened in this diagram? So explain the function of this diagram and COP of the simple air refrigeration system, etc. Let's start the working function of this system. The outside ambient air, that is at high altitude, which comes inside this diffuser. By here we use diffuser component. So we use a diffuser component here. So this process is known as a ramming process. So let's take a point number 0. Let's take given point 1. This is 1 to 2 process, that is a ramming process. Name is a ramming process. 1 to 2 process is a ramming process. 1 to 2 process ramming process, and this process, this is a isentropic compression process, or we can say isentropic compression or diffuser. We use diffuser use the pressure is increases because atmosphere outside ambient pressure is less than barometric or atmospheric pressure. That's why we increase the pressure of this ambient air or outside air. So we use diffuser here, and this process is known as a ramming process. 1 to 2 takes place. Then this ramming air is passed into the main compressor in the aircraft. In main compressor, this ramming air is compressed at high pressure, and then some amount of air is passed into the heat exchanger, and remaining amount of compressed air which is passed into the combustion chamber, for combustion of the fuel, and remaining some amount, that is mass of air, we can say mass of flow rate of air, which is passed into the heat exchanger, which is highly temperature of this air is very high. So temperature is very high, and in passing through the heat exchanger, so here heat is transferred from ram air to this air. So how to heat exchanger this work? So some amount of ram air comes into this heat exchanger, which is temperature is less than air comes from the compressor. So that's why temperature of ram air is absorbed from this high temperature compressed air, which is flowing into the heat exchanger, which gives their heat to this ram air. Okay, so that's why temperature of this compressed air decreases. That's why we use the heat exchanger. But pressure is almost constant, because in heat exchanger pressure is a constant. So after compressor, pressure is very high. So we want to decrease the pressure of this cold air. So we use the turbine. So turbine is work is like to decrease the pressure. If pressure is decreases here, so temperature is automatically decreases, because we can say cooling turbine work as a isentropic expansion process. Okay, isentropic expansion process. If pressure of this air decreases, temperature is also decreases. Then this air, how much amount of pressure is decreasing? At like atmospheric or ambient pressure, like 1 bar, around 1 bar pressure, and this cold air is supplied to the cabin of aircraft. This cold air is supplied to the cabin of aircraft. In cabin, this air takes heat from occupants, electrical device, or etc. or engine. That's and is again flow out to the atmosphere. Okay, this turbine is work from this cooling fan, and this cooling fan is work on this rammed air, which is comes from the heat exchanger after taking the heat from this compressed air. Okay, so let's start. How many processes takes place in simple air refrigeration system? This is 1 to 2 process, that is known as a ramming process. Okay, and this is 2 to 3. Here 2 to 3, that is a compressor. Isentropic compression process. Isentropic compression 2 to 3. After ramming 2 to 3 and 3. So here point number 3 is here and point number 4 is here. 3 to 4 is a constant pressure heat exchanger process, and next is 4 to 5 after cooling turbine. 4 to 5 is a turbine process, and then 5 to 6. In some books, sometimes written as a 0 to 1 process. Sometimes in some books written this is 0 to 1 process, that is a ramming, and 1 to 2 is a compressor process, and 2 to 3 is a heat exchanger process, and 3 to 4 is a turbine process, and 4 to 5 is a cabin process. Okay, so temperature at 5 is a more than temperature of 4 because of it takes heat from the cabin and it's throughout from cabin to atmosphere. Okay, so what happened all the process? 0 to 1 is a ramming process, and 1 to 2 is a isentropic compression process, and 2 to 3 is a constant pressure heat exchanger process, and 3 to 4 is a isentropic expansion process where pressure and temperature decreases in the turbine, and turbine which runs the cooling fan connected by the cooling fan. This fan is rotated by with the help of ram air. Okay, so this is a work of cycle, and this all the process draw in the TS diagram. Let's see the TS diagram. Okay, so here TS diagram is 0 to 1. Okay, 0 to 1 process. This is our 1 and this is our 0. 0 to 1 is a isentropic compression, and 1 to this is our ramming, or we can say ramming, and 1 to 2 again compressor isentropic compression where temperature and pressure both are increases because it is in a main compressor. That's why 1 to 2 process. Here work is supplied to the compressor. Next 2 to 3 process. In this diagram we see 2 to 3 is a heat exchanger, and here pressure is a constant. In heat exchanger pressure is constant, but temperature is decreases because we use heat exchanger. It loses our heat from ram air, and ram air is colder than this compressed air. Then this 3 to 4 compressed air out from this heat exchanger, their pressure is very high. So our aim is to decrease the pressure about to 1 atmospheric. That's why we use cooling turbine. But pressure is decreases, that time temperature is also decreases. So temperature T3 to T4 decreases, and then 4 to 5 process is a cabin process where this cooled air is passing in the cabin. This is our cabin effect or cabin process, or we can say this is our desired refrigeration effect. Refrigeration effect, because at 4 point entry in the cabin, at 5 it's a throw out from aircraft. Okay, so 4 to 5 the temperature, but obviously temperature of 5 is more than temperature of 4. Lowest temperature in the cycle is a 4. Okay, sometimes 0 is also lowest temperature because outside of temperature is a very less, but pressure is a very less and temperature is also very less at high altitude. Okay, so next 0 to 1 process. So let's start to calculation and calculate the COP of the simple air refrigeration system. 0 to 1 process is ramming process, and 1 to 2 is a compression process takes place in the compressor, and 2 to 3 is a isobaric heat exchanger process where heat is exchanged to the ram air. Okay, 3 to 4 is a cooling turbine process, and 4 to 5 final, there is a refrigeration effect, or we can say cooling process, or we can say cabin effect. Okay, so here also we draw a diagram which is already explained in the previous slide. Okay, so let's calculate the COP. Suppose assume that if V is the velocity of aircraft, V is the velocity of aircraft or velocity of air relative to the aircraft. Suppose it is our aircraft. Okay, V is the velocity and relative velocity of this outside air and contact with this aircraft is the V velocity, meter per second. Then kinetic energy of outlet air relative to aircraft. What is kinetic energy of the aircraft? Which is relative kinetic energy, that is the half of mv square. So it is converted. So we use, that is a v square. How it comes from SFE, steady flow energy equation, H1 minus H naught, because this outside air is take place 0 to 1, that is a ramming process. So 0 to 1 process, that is a ramming. This process outside air comes into the aircraft, that is H1 minus H4 is equals to V2 minus V square divided by 2000 kilojoule per kg. Now H is converted into MC delta T. We can use MCT because of ideal air case is used, so that's why we converted into CPT. CP specific heat of air, and T1 is the temperature in the when air is comes into the diffuser. Okay, and minus CP T naught. T naught is what? Outside temperature. Air is comes into the aircraft into the aircraft. And V square is the relative velocity of air compared relative to aircraft in kilojoule per kg. So now it's is equals to T1 is equals, so by simplification T1 is equals to T naught plus V square divided by CP 2000. Okay, so by using of this formula we can calculate the temperature of T1. So other method is also we have 0 to 1 ramming process. This is isentropic process. Because it is isentropic process, we can use the formula T1 by T naught is equals to P1 by P naught raised to gamma minus 1 by gamma. This formula is already we have studied in the reverse Brayton cycle or in thermodynamic also, because process is isentropic. If process is isentropic, so we can write this formula, because how this formula comes, PV in H2, gamma is constant, apply for 0 to 1 process, and this formula is proved. Okay, so remember this formula. By using of this formula, we can also calculate the temperature of at point 1. Okay, next is 1 to 2 process, air compression process in main compressor. That means this process is compression process. Work or power supplied to compressor per kg of air. How much amount of work which supplied to the compressor to compress for compression of air? So that is a P, that is P is equals to WC is equals to MA Cp T2 minus T1. What is MA? MA is mass of air, Cp is specific heat of air, T2 temperature of after compression, and T1 is temperature before compression, that is WC. That is also power supply. Next is 2 to 3. 2 to 3 process is cooling turbine or cooling of air by ram air in heat, not turbine, cooling of air by ram air, because in heat exchanger, ram air is supplied to cool the compressed air. To cool this compressed air, ram air is supplied. So it works as a heat exchanger. But in heat exchanger, pressure is constant. Okay. So how much amount of heat absorbed from compressed air, that is a QR, MA Cp minus T2 minus T1. T2 is what? Before inlet in the heat exchanger. T3 is what? After heat exchanger. That is a T2 is more than T3. That's why we written as here T2 minus T1. Next is 3 to 4 process. What is 3 to 4 process? Isentropic expansion of air in cooling turbine. And because of it is isentropic expansion process, we also use this formula T3 by T4 is equals to P3 by P4 raised to gamma minus 1 by gamma. So by using of this formula, we can calculate the temperature T4, or we can also use this formula work of turbine, which is turbine work which we obtain the turbine work WT is equals to MACP T3 minus T4, and for calculation of T4 we already explained this formula. By using of this formula we can calculate T4 value. Now 4 to 5 process. 4 to 5 is what? Refrigeration effect, where it takes place in the cabin. Refrigeration effect takes place in the cabin, because from turbine, cooling turbine, the cooled air is supplied in the cabin. That is a point number 4 before supplying into the cabin, and point number 5 is what? After cabin. Okay, that's how much amount of heat is absorbed from the cabin. That is a QA is equals to Cp T5 minus T4. That is our the refrigeration effect. That is our refrigeration effect, and this is heat losses by heat exchanger. Okay, so remember this formula. Next is refrigeration capacity. What is refrigeration capacity? There is a QA. This is our capacity also. We can say if we multiply with mass, total mass flow rate, so it converted into the refrigeration capacity. What is difference between these two? Refrigeration is effect in comes into the kilojoule per kg, but refrigeration capacity comes into the only kilojoule because mass is supplied, and refrigeration capacity is nothing but that is the capacity of the aircraft refrigeration system, or in terms of reverse Brayton cycle capacity of the plant if we multiply mass of air. Okay, this is the main difference. This is our TS diagram which I already explained. Now if Q turn of cooling load of cabin is given, if Q turn of cooling load of given, that means we already now explained in previous slide, that is a Q is equals to MA CP T4 minus T5 minus T4, because T5 is more. This is our capacity, refrigeration capacity of the aircraft system, refrigeration system. But you know the Q turn या QTR, that means QTR capacity is given mass of air Cp T5 minus T4. We can use this formula so that mass of air flow rate which we can calculate as a QTR divided by Cp T5 minus T4. But 1 ton, we know that 1 TR is equals to 3.5 kilowatt, or we can say 210 kilojoule per minute. So by use of this formula, we can calculate final mass flow rate of the system. Mass of air is equals to 3.5 Q divided by Cp T5 minus T4, or we can say in kilojoule per minute, mass flow rate kg per minute. So we use the 210 Q divided by Cp T5 minus T4. This is our formula. Clear everyone? So let's check formula. Refrigeration capacity we already know. So we use this formula MA 210 Q Cp T5 minus T4 kg per minute. But it want to convert it into the kg per second. So we use the formula 3.5 multiply with the 3.5 Q, which is in numericals you already given 12 TR, 12 ton, 15 ton, 16 ton, 6 ton. Just put the value of Q here and calculate the mass of air. Now COP of the system. What is the COP of system? That is the refrigeration effect divided by power of compressor. So in TS diagram, where is refrigeration effect? This is 5 to 4 or 4 to 5. Or where is compressor work? This is 1 to 2. So we use this two formula, compressor work and this is refrigeration effect. So final formula of COP is like this. But in this derivation we neglect the turbine work, so we not minus WT, WC minus WT, but in Brayton cycle, in reverse Brayton cycle we do WC minus WT. So here turbine work we neglect here. So next cycle is simple air refrigeration system with evaporative cooling. So this is our cycle, how it works, same like previous cycle, but here one component are added, that is the evaporator. But evaporator is similar like a heat exchanger. The heat evaporator are added, but same process, that is a 0 to 1 process. Ramming outside air comes into the this duct or diffuser. We use here diffuser. That's why pressure increases, but process is isentropic. And then this 1 to 2 process is a main compressor process where pressure of air increases. If pressure increases, temperature also increases. The process takes place here is a isentropic compression. Next 2 this 2 point air is going into the heat exchanger. There is 2 to 3 heat exchanger. How this heat exchanger work? 2 to 3 is a heat exchanger process where heat is given off by ram air, where ram air is supplied from the here. Okay, so this compressed air loses their heat to ram air, and this low temperature compressed air is passing into the evaporator. In evaporator also temperature decreases. Also temperature decreases with the help of water, supply. After water, it takes heat from the high pressure compressed air, so water is converted into the vapor form. And this low temperature high pressure air is passed into the cooling turbine. What is the function of cooling turbine here? That's reduce the pressure approximately like ambient pressure, or we can say atmospheric pressure up to 1 bar. Okay, 1 bar, approximately 1 bar. So this pressure, low pressure, we reduce the pressure of this air, so it transfer to the cabin. Okay, it transfer to the cabin, where cabin it absorb the heat from cabin and throughout from this aircraft. Okay, this is the total cycle. This cooling turbine is drive this cooling fan to remove this ram air, Okay, so total pressure we already again discussed. 0 to 1 is a ramming process. This is 1 to 2. This is 1 to 2 is a heat exchanger process. This is 1 to 2, and 2 to 3 is a heat exchanger. 3 to 4, this is 3 to 4 is an evaporator process, and 4 to 5 is equals to cooling turbine, and 5 to 6 is equals to refrigeration effect or cabin effect. Just remember all the process: 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5, and 5 to 6. And remember that ramming process is isentropic process, and compressor is also isentropic compression process, and 2 to 3 is a constant pressure heat exchanger, and 3 to 4 that is an evaporative process, or we can say constant pressure evaporation process. And 4 to 5 is a cooling turbine, which is used to reduce the pressure, but pressure is reduces, temperature is also reduces for ideal case. Okay, or ideal air, because air we assume as a ideal. Next, this is our TS diagram for this. Okay, 0 to 1 similar like previous TS diagram, just difference is 3 to 4, extra 3 to 4, because at constant pressure temperature decreases. Again 0 to 1, this is 0 to 1 is a ramming process, and 2 to 3 is a compressor process where pressure is increased, and 2 to 3 this is 2 to 3 process, heat exchanger process, where it loses heat but pressure remains same because constant pressure device. 3 to 4 work as a heat exchanger where heat is decreases, and 4 to 5 is a cooling turbine process. 4 to 5 is a turbine process where entropy is a constant but temperature decreases. If temperature decreases, pressure is also decreases. And 5 to 6 is equals to cabin process or cabin effect. Now, how to write the COP? So in previous article we write the COP of this formula. If QTR is given, refrigeration capacity MACP T6 minus T5. In previous slides we also derived that T5 minus T4. Just one step is more because of heat exchanger, because of evaporator are added. That's why only changes is here refrigeration capacity formula. T6 minus T5. That means T5 minus T4 replaced by T6 minus T5. That's only changes in formula. Everything is same. Okay. Next is Bootstrap refrigeration system, which is used in the aircraft. So this is our Bootstrap refrigeration system, and number of time, this is very most important because of number of time in exam this is asked. Bootstrap refrigeration system. In this system, 2 compressor are used. Main difference from previous is 2 compressor are used, 2 compressor and 2 heat exchanger, not evaporator. Okay, let's start to discuss how it works. Ambient air, that is the outside air, where pressure is approximately we can say 0.8 bar or 0.5 bar, because at high altitude pressure is very less. So we want to increase this pressure, that's why we use the diffuser in the aircraft. So air comes inside the done. So pressure is increased. Because of pressure increased, temperature is also increased, because this process is ramming process, or ramming process is isentropic process, and then this rammed air is passed into the main compressor. In main compressor, compressor is increases. If pressure is increases, temperature is increases, because the process is isentropic compression process where entropy of the system is constant. So in compressor, entropy is constant, pressure increases and temperature increases of air. Okay, ramming air. Next, after compression, this compressed air is flowing into the heat exchanger, where heat is given to the ram air, because of some amount of ram air passed in heat exchanger 1, because here we use the 2 heat exchanger 1, this is our heat exchanger number 1, this is our heat exchanger number 2. So for heat exchanger we use this ram air as a fluid, so heat is given off by compressed air to the ram air in first heat exchanger. After this decreased temperature is decreases, after this compressed air and flowing after heat exchanger supply to the secondary compressor, where pressure is also increases and then temperature also increases. That's why we use secondary heat exchanger. So temperature is decreases in secondary heat exchanger. Why we use secondary heat exchanger? Because before secondary compressor are used here in between two heat exchanger. So here temperature is increases and pressure is increases. That's why we reduce the temperature of this system. We use a secondary heat. That's why we use secondary heat exchanger. And after that, here pressure is very high. Okay, temperature is low, moderate, low, and this is passed into the this cooling turbine. So here pressure is decreases around 1 bar and temperature is also decreases. That is a temperature very low, like 20-25 degree, and this is transferred to the cabin. So in cabin, heat is absorbed from the cabin, from occupants sitting in the cabin, aircraft cabin, or we can electrical device or etc. Okay, so now this turbine is work is transferred to this compressor. This compressor is driven by this cooling turbine. Just remember, secondary compressor is driven by this cooling turbine. This is the main working function of Bootstrap refrigeration system. Okay, so total process cycle is, let's start process cycle. That is a 0 to 1 ramming, and 1 to 2, 1 to 2, that is a isentropic compression. There is a 2 to 3. 2 to 3 is first heat exchanger, where heat is exchanged to ramming, and 3 to 4. 3 to 4 is nothing but secondary compression, that is isentropic compression, and 4 to 5 is a secondary heat exchanger at constant pressure, and 5 to 6 is a cooling turbine, where pressure decreases and temperature is also decreasing. And next is 6 to 7. 6 to 7. Okay, 6 to next is 6 to 7. This is a 6 and this is a 7. So where heat is absorbed from the cabin. This is the total process. Okay. So here in this diagram, the process are showing 0 to 1 is a ramming process, but here some irreversibility process are showing. That's why we denoted by the dotted line 0 to 1 days. 0 to this is dotted line 0 to 1 days, and again 1 days to 2 isentropic compression, 1 days to 2 days. If it is theoretical, that is a straight line, but it is not a theoretical due to irreversibility. This is this line, so work required is a more compared to theoretical. That's why we denoted by this days line here. Okay. Now 2 to 3. 2 to 3 is nothing but 2 days to 3 is nothing but it is a heat exchanger process. First heat exchanger process. 2 to 3 or 2 days to 3. It is a first heat exchanger, that is cooling process, and again 3 to 4 is a compressor number 2, secondary compressor, or we can say 4 to 3 is a compressor. But if it is takes place due to irreversibility, 3 to 4 shifted like here. Okay, 3 to 4. Next 4 days to 5. 4 days to 5 is what? 4 days to 5 is a turbine. 4 days to 5 is our secondary heat exchanger. 4 days to 5 is nothing but is a secondary heat exchanger where temperature of the air is decreases but pressure remains same. Pressure is constant whatever is there after compressor, secondary compressor. Okay, next 5 to 6 is what? 5 to 6 is cooling turbine. Why it is a straight line? Because of theoretical process, isentropic expansion process. That's why this draw as a straight line. And this is the dotted line which is shows that this is an irreversible process and work of turbine is less than theoretical. Work of turbine is less than work of turbine of theoretical. That's why we draw as a dotted line. Okay. This is 6 days, and 6 to 7 is a cabin effect or refrigeration effect, and pressure is a same. That's why, because of cabin is a pressure is the same. That is the refrigeration effect. Next, this is our TS diagram which is explained in previous slide, and if QTR is given for the load of the cabin, so refrigeration capacity QA is equals to mass of air into Cp T7 minus T6. Just changes, one step is more here, T6 minus T7. But in the numericals, given that efficiency is given there, so we use turbine efficiency is given, so we use T6 days minus T7, not T6 minus T7. Just remember T6 days. If whenever efficiency is given, we use the actual formula or 6 days formula. Next is mass of air, how to calculate, converted into the QTR is given, so 210 Q. If asked in the kg per second, so we put 3.5 kilowatt is equals to 1 TR. So now COP is same is previous, just numerator are changes. This is the COP of the Bootstrap refrigeration system, which whatever it is 3.5 Q, that is the capacity. 3.5 is nothing but that is the capacity of the refrigeration system. The P is a power, that is a work of compressor. So thank you so much guys.